Good morning. That is fuzzy all of a sudden. That was better before. Maybe if I move my hand under here. Whoa, that's kind of weird. So if there we go. Now it's in focus. We're going to look at 17.5 today. Some molar entropy calculations. Notice entropy, not enthalpy. These are going to be in joules per mole Kelvin, not kilojoules per mole Kelvin. Entropies tend to be smaller values than enthalpies. So they're usually in joules, but you do end up multiplying them by temperature oftentimes when you use them in other things. So those temperatures are large numbers, so it kind of balances out and that kind of stuff. But these are values you can look up in the back of the book or on the references on OWL. So let's say they ask for a specific one. They want to know what's delta S for this reaction. Now, in general, we're going from 2, right? Don't forget to balance. 2 hydrogens and 1 oxygen to 2 water. So I'm going from 2 elements to 3 total elements to 2, but it's a compound kind of thing. So you might have a harder time saying, well, is this going to be a positive delta S or a negative delta S? Everything's a gas, all that kind of stuff. We know it's exothermic, right? We know it releases heat energy, but is it getting less random or is it getting more random or what, right? So you might have your predictions on that, but let's go ahead and do the calculation so we can actually see it. So just like when we did delta H's, delta S is going to equal products minus reactants. And I'm left-handed, so you can't see anything that I'm writing. So products minus reactants. So I'm going to do 2 times the water. So if we look at water's randomness, right? It's entropy as a gas. That's 188.8. Notice that is a lot more random than water as a liquid, right? That's a big difference there. So you got to make sure and pay attention to states. So 188 joules per mole Kelvin. And we will subtract that from 2 times hydrogen. Hydrogen is a pure substance. And it's only an element, but it's not a pure crystalline solid at 0 Kelvin kind of thing, right? So it's not going to be 0 entropy. I can't talk today. So 130.6 joules per mole Kelvin. Joules per mole Kelvin there. And to that, we will also add oxygen, which is 205. Joules per mole Kelvin. So we start to see that and you see, well, there are 2 of these waters and the water is a pretty good value here, but, overall we're going from 3 gases to 2 gases. So, we can see where we're going to end up positive, negative wise, right? So 2 times 188.8 minus, be careful with your parentheses there because we need the whole thing, 2 times 130.6 plus 205. Not a bad idea to do that calculation yourself. It's easy to get parentheses in the wrong spots or whatever. And when we do that, we end up with a negative 88.6 joules per mole Kelvin. So that's my delta S. That tells me it is getting less disordered. It is getting more ordered, because we went from 3 gases to 2 gases, not a massive change, but a change. So this is working against the reaction taking place. So it's exothermic, so the heat is going to work towards it happening, but the randomness is going to actually work against it happening because you are going from 3 pieces to 2 pieces there. Right? But we can calculate those delta S's. So this is a reaction that is becoming more ordered as we do that. Right? But as you kind of start to see what we know that that's a reaction that happens. So how do we put that together mathematically with the idea of enthalpy? So we know it needs an activation energy, but we know overall this is a spontaneous reaction, right? We know it's overall spontaneous. So delta G on this thing must be negative, because a few slides ago on the last one, we saw spontaneous processes have a negative delta G. Well, this is spontaneous. Now, it needs an activation energy, right? You have to provide it a spark, but overall it releases energy, total energy, but the delta S is working against it. So mathematically, how do we put those 2 ideas together? So if we're looking at these 2 mathematically, that's 17.6 in our book. And this is probably the biggest single equation that we're going to use for this unit, right? And that's delta G equals delta H minus T delta S. So notice you get a sign flip there because like a negative delta S was not leading towards spontaneity, but a negative delta G is spontaneous. So you get this negative here, and then you are going to multiply that by the temperature. So that's going to make those smaller, like 100 joules per mole, start to match up a little closer to the kilojoules per mole. The higher the temperature, the more important the randomness becomes. The lower the temperature, the less important the randomness becomes, right? Now it's kind of where we talked about ice freezing and melting. At some temperatures, ice freezing is spontaneous, and at other temperatures, ice melting is spontaneous, right? And that's because you get this temperature factor lumped into this whole thing, right? So we've got heat energy minus temperature times randomness energy. So we'll look at some specifics. So we just want, will this reaction occur spontaneously at 298 Kelvin? We know our delta H for the reaction. This is, go ahead and quiz yourself for real quick. Is this endothermic or exothermic? And then is it overall becoming more ordered or less disordered? So which of these is moving towards spontaneous? Which of these is not moving towards spontaneous? So this is exothermic. So that is moving towards spontaneity. This is going to release heat energy. That's going to help drive this reaction to happen. Delta S is more ordered. So that is moving towards it not happening, right? So here we're going from two different types of solids to one type of solid, right? You're going from copper 1 sulfide and sulfur to copper 2 sulfide. So delta G equals delta H minus T delta S. So delta G is going to equal negative 26.7 kilojoules per mole minus the temperature is 298 Kelvin times negative 0.0197 kilojoules per mole Kelvin. Notice we need to change joules and kilojoules to be the same. So either change both of them to kilojoules or both of them to joules. I tend to change them both to kilojoules because otherwise you're going to end up with really big joule numbers. But it doesn't really matter what you do there. So negative 26.7 minus 298 times 0.0197. Orders of operation isn't a big deal, so I don't have to worry too much about that. And there was a negative. Whoops, I typed it into my calculator wrong. I only put one of the negatives in there, so I ended up with the wrong value. So negative 26.2 minus 298 times a negative 0.0197. So that's going to give me a negative 20.8 kilojoules per mole. So it is spontaneous. Whoops, the delta G. It is spontaneous. It should happen. It should release energy overall. Biology folks like to call it exergonic reactions. We don't really use that term in chemistry. We just say it's got a negative delta G, right? It's releasing energy overall. It is exothermic because of the delta H, and it is becoming more ordered as far as the delta S. All right, so there's this whole thing together in stuff you can actually read. Right, so we take a look at how we can do this Gibbs free energy with Hess's law too. Just like we could do delta H with Hess's law, we can do delta G with Hess's law. So if I want to go from diamond to graphite, right? So I go from diamond to graphite. I'm going to rearrange these. So I'm going to leave this one as is, and I'm going to flip this second one. So if I flip the second one, that's going to be CO2 changes to O2 plus graphite, carbon, graphite. I'll use a G. Well, I'll use a GR so it doesn't look like gas. Right? When I do that, my CO2s cancel out. My O2s cancel out. Right? Because they're on opposite sides now. And so I have diamond going to graphite. My delta G, I need to flip. So that's going to become a positive now because we flipped the sign. So just like on delta H stuff when we did Hess's law, I can add these reactions up. And so going from diamond to graphite, if I add those up, is going to be a negative 3 kilojoules per mole. So that will release energy, which means it is spontaneous. So it is spontaneous for diamonds to go to graphite. That doesn't mean it happens, and it doesn't mean it happens quickly, right? So that's the whole, yeah, it is technically a negative delta G, but it has a very high activation energy, so it does not happen quickly or relatively at all. I mean, it happens, but it's over the course of like a million years or something like that, right? So diamonds aren't really forever. It is spontaneous for them to burn and for them to turn into graphite and all that kind of stuff. It's just hard to break those bonds and actually shift that stuff around, right? So it should be spontaneous, but kinetics rule this reaction, and so it doesn't really happen at any normal rate kind of thing. All right, so overall, energy, well, that's probably about enough for today. Yeah, make sure and work some OWL problems today. This delta G equals delta H minus T delta S stuff. Let me get back to that slide. This one is a pretty big deal. We need to work quite a few problems on that, make sure we understand that. Those problems can be kind of challenging, right? If they have you look up the delta H's for that problem, look up the delta S's for that problem, and all those, there's a lot of different kind of ways we can do that. So start working on those problems. Swing by the Google Meet if we need help with working any of those problems. We can jump on and look at those together. That's not a problem at all. So anyway, have a good one.